Welcome back to our CNT 140 class, LAN Wiring, Chapter 14, Telecommunications Rooms and Wire Management. In this lesson we're going to be highlighting the telecommunication rooms, horizontal and backbone wiring, accessibility and appearance, room size requirements, power requirements, backbones and concentration. Now the concept of a series of interconnected telecommunications rooms is central to structured cabling system design. The planning and placement of these telecommunications rooms is a subject sufficiently important for Telecommunications Industry Association, the TIA, to devote an entire standard to it, which is the 569-B Commercial Building Standard for Telecommunications Pathways and Spaces. In this chapter we're going to discuss the placement of telecommunications rooms in modern telecommunications installations. Naturally, this discussion will center around designing a wiring system for LAN use. This will impose some additional considerations on the location of our telecommunications room, primarily because of the distance restrictions of LAN wiring. Defining the TR. The telecommunications room is more broadly defined in the 569-B as a hierarchical system of telecommunication spaces that are used for the concentration and connection of a building's telecommunications wiring. This standard covers wiring space for all telecommunications activities and actually includes telephone as well as computer wiring. Now, because of the much lower operating frequency, telephone wiring is not subject to the severe distance limitations of LAN wiring. For example, the standard allows a total of 800 meters for an unshielded twisted pair circuit run through a combination of telecommunications rooms, far beyond that allowed for a single LAN, which is limited to 100 meters without passing through a repeater or bridge. So we'll concentrate on criteria appropriate for LANs and assume that telephone wiring will either easily meet its requirements or be separately handled. So let's look at traditional cabling hierarchy. In this hierarchical telecommunications room system, so-called structured wiring, there are three types of closets: the telecommunications room, the intermediate cross-connect, and the main cross-connect. As the figure shows this hierarchy, the structure does not assume that any of these telecommunications rooms necessarily contain equipment such as hubs or telephone gear, but allows for any telecommunications room to be collocated with an equipment room. In the traditional structured wiring installation for telephones, a cable from the local exchange carrier would enter the building and run to the main cross-connect, which would generally allow or also house the user's telephone switching equipment. This would be a combination MC and equipment room. Cross connections would be made between the LEC, the local exchange carrier, lines and the telephone switching equipment, and additionally between the telephone switch and large multi-pair cables running to the ICs or TRs on each floor. A large building would have intermediate cross-connect spaces where the multi-pair cables will be terminated and split out to their feeder cables to TRs near various office locations. At the TR, the station cables from each workplace location would be cross-connected to the feeder cables. The line for each phone would actually be connected through the TR to the IC and to the MC, and then finally the telephone switch. In a smaller building, the functions of the various closets would be combined. In a very small building, all connections might be made in one space, a combination TR, MC, and equipment room, ER. Fitting the LANs into the structured cable hierarchy. LAN wiring is implemented on basically the same scheme, but with several important differences. First, the LAN systems are distributed systems. There's no large central device similar to the PABX from which all the connections emanate. Instead, the connections are made to hubs located in the telecommunications room, thus a TR, ER. Then, as we're going to see, the hubs are interconnected to each other and to common resources such as servers. Now, with regard to LANs, telecommunications rooms are usually interconnected with no regard to hierarchical levels since the network components are distributed. Still, the telecommunications room hierarchy is a useful model. So let's take a look at the horizontal and backbone wiring. All the wiring from workstations to telecommunications rooms and between telecommunications rooms is referred to as horizontal wiring and backbone wiring, respectively. And in the terminology of structured wiring, backbone wiring is sometimes called vertical wiring. If we envision workstations on each floor of a building and wiring closets vertically stacked with one per floor, this terminology does make sense. However, multiple telecommunications rooms are often located in the same floor, so the term backbone is clearer than the term vertical. The wiring from workstation telecommunications room is the horizontal wiring, and the wiring between the rooms is the backbone wiring. If we also have additional telecommunications rooms, such as the intermediate and main cross-connect rooms, the wiring between those rooms is called backbone wiring. This terminology holds whether the rooms are on multiple floors or are on the same floor. The TIA standards always use the term backbone to refer to wiring between telecommunications rooms. And unfortunately, backbone has a very different meaning in LAN systems as compared to telephone. A LAN backbone is a logical subdivision of a network that has nothing to do with where the wiring goes. And in fact, wiring on the same LAN backbone segment can be in 2 or more telecommunications rooms, or 2 LAN backbones can be in the same telecommunications room. However, we will stick with the wording in the standards that refer to all wiring between telecommunications rooms as backbone wire or cable, unless we're specifically referring to that portion of a LAN system that interconnects multiple LAN hubs or bridges. Color coding for the telecommunications room. 569B recommends that the cross-connect in the telecommunications room be grouped together and prescribes a color code to further show this grouping. Table 14.1 behind me shows the recommended colors for various terminations and cross-connects. For the cross-connect locations, the standard generally uses traditional colors such as orange for the telco demarcation punch blocks and blue for the station cable punch-down locations. Actually, the punch block itself is usually white, but its cover or mounting board may have the color code. The standard also recommends that different jacket colors be used on the cables to distinguish between the usage types of cables. This presents an interesting dilemma, as the colors in the standard bear little resemblance to the traditional colors used in commercial cabling. For example, station wire to the workstation has traditionally been run in beige or gray in the plenum rated default, but the standard shows blue for this use. The color gray is used in the standard, but only for second level backbones from the IC to the telecommunications room. Many LAN installers would agree that there is an advantage to having the LAN cables a distinctly different color from the telephone cables, but the standard assigns the same color to both types of station cables. Of course, if the telephone cable is simply run in a traditional color such as gray despite the standard, then the LAN cables may be run in the recommended blue color to distinguish them from the telephone cables. However, in a design that includes both telephone and LAN cabling, you could not simply specify that the TIA standards be used in your statement of work, because a telephone cable color would not be in compliance. Frankly, it'd be easier to just use traditional colors for all the telephone wiring. Intercloset cables are easy to recognize because they have distinctly larger pair counts and are consequently physically much bigger than the station cables. You can adhere to the color code at all points of termination or interconnection for the telephone system, since many cabling veterans strongly recommend keeping LAN wiring completely separate from telephone wiring. The use of contrasting blue LAN station wire is appealing, and you could allow a deviation from the cable color recommendation for the telephone wiring, but would maintain color coding for the LAN cable. So making your horizontal runs. How many horizontal cables should you run between telecommunications rooms into the work areas? The standards state that you should run 2 cables to each individual work area, but is that going to be enough? The answer to the question depends on many factors, but the 2 most important considerations are growth and utility. You must determine what amount of growth planning is reasonable and what it will cost to implement. For example, if you have large individual offices that may eventually include 2 workers, overwiring by a factor of 2 will be reasonable. The type of work that is to be done is also important. For example, some workers may eventually need 2 computers or 2 phone lines. In such cases, you should provide at least 1 additional station cable outlet that can be used for expansion. Generally, it's far less expensive to do a certain amount of overwiring during initial construction than it is to add the outlets later. So what method should you use to terminate the cables in the telecommunications room? The answer to this question depends on whether you intend to install a universal wiring system where any cable can serve your telephone or LAN system, or install separate telephone and LAN wiring systems. Telephone wiring is quite forgiving in that you may run longer distances and make a larger number of cross-connects between the telephone instrument and the switching equipment. Modern LANs are much more restrictive in this regard. Early cabling standards allowed 2 cross-connects for a single LAN connection, but the latest Cat 5 through 7 wiring standards as shown behind me, allow only one cross connect and also severely restrict cable lengths, including that for the cross connect wire. Now this is to allow for the strict attenuation delay and crosstalk limits of 100 MHz and higher networks. Many experts even recommend that the workstation cables be terminated directly into a patch panel with no ICs at all. One of the reasons for this cross-connect limit is that all wiring terminations require that the pairs be slightly untwisted to be punched down at the point of termination. When the cable being used is very tightly twisted, as with category 5E through A6, this untwisted portion increases the crosstalk, introduces noise, disturbs the line impedance, and increases the RF emissions. Too much untwist can cause a link to fail at the higher LAN data rates, especially if the cable run is near the allowable length limit. All punch-down blocks introduce untwist into a link. The extent of the problem is less with the 110 style blocks than with the older 66, but it exists nevertheless. The effect of untwist is more disruptive as the network speed increases. Terminating the station cables directly onto a patch panel minimizes the amount of untwisted wire and increases the performance of the link. So distance considerations. The primary guideline in locating telecommunications room is to place them near the work area that they're going to serve. Advisory language in the standards says to place them in the center of the area to be served, but this central location is simply impossible in many existing buildings. The layout of the building may cause you to have to run your cables from a telecommunications room location on one side of the floor to each of the workstations. In some cases, it's critical that you predetermine the lengths of the wiring runs. And those runs exceed the appropriate limits, additional telecommunications rooms will be needed. In new construction, the architect should be given firm instructions as to the placement of infrastructure facilities, such as telecommunications rooms and equipment rooms. And if you make these needs known at the inception of building design, you will be more likely to have the telecommunications spaces that meet standards. You should give consideration to placing the telecommunication rooms vertically over the other so that wiring distance between the rooms will be minimal. In large buildings, multiple utility shafts not only simplify telecommunications wiring, but also eliminate the single point of failure in single shaft designs. The benefits of this approach go beyond the telecommunications issue. It is also a good idea to provide an orderly system of cable ducts or sleeves, both for interfloor and firewall use. Proper ducting will allow workers to place the UL-rated fire-stopping material in the ducts and enhance the fire protection. Also, because many utility shafts are closed in reinforced concrete structures, this avoids the problem of random wall penetrations and sneaker cables that are forced alongside existing pipe and HVAC penetrations. The maximum drop length. LAN wiring standards dictate strict distance limits for horizontal cable runs. These cable drop lengths include the entire cable from the point of termination in a telecommunications room to the workstation outlet. Standards also cover the maximum distances between the telecommunications rooms. In this way, the requirements of the 568C and 569B work together in balance with the building's architecture to achieve a compliant wiring system for your LAN that will meet your needed performance. The maximum length for horizontal cable is 90 meters. This 90-meter length excludes the user cord that connects from the outlet to the workstation or telephone instrument, and the patch cord or jumper that connects from the patch panel or cross-connect field to a hub or other device. Now, this is the maximum acceptable length and not simply an average length or a goal. You should try to keep your wiring well below this length in most cases. At least two telecommunication outlets must be provided for each individual work area, although some of the lower speed LANs such as 10BASE-T and even Token Ring may run to longer distances of as much as 150 meters. Exceeding the standard intentionally is a bad idea. You cannot expect such run lengths to support 100 meg or gig data rates at all, and any equipment problems will be blamed on the excessive drop lengths. As a matter of fact, cable testers are required to fail a basic link longer than 90 meters, allowing for test cables and measurement accuracy. For a complete discussion of measuring cable lengths using cable testers, you will see that in Chapter 15. The allowable backbone cable distance between telecommunications rooms depends on the type of cable you use as well as practical considerations. For example, the standard allows 2,000 meters from TR to the MC for fiber optic cable, but only 800 meters for unshielded twisted pair. The distances are even less between the inner cross connects and the other two types of telecommunications rooms. However, a practice may dictate much smaller distances if you wish to connect between two telecommunications rooms on a 100 base T or a gig link. For example, you'd have to limit the backbone run to the same 90 meters that you're limited to for any hub to workstation link. As mentioned previously, although some situations may operate with slightly longer cable lengths, they do not meet the requirement for inevitable higher speeds of 100 meg or more. The estimated drop length, cable drops from the proposed telecommunications room to the workstations to be served, must be within the maximum allowable length of 90 meters. You should estimate these distances before finalizing your cable system design. If the estimates exceed the maximum length, then you need to add one or more wiring closets, although there are minimum size specifications and features for telecommunications rooms, which we'll talk about later. You may be justified in putting in a substantial or a substandard telecommunications space to get the drop lengths down. To estimate the total length of a cable run, you must first know how the cable will be routed and hung. Conventional wiring is often routed through metal floor or roof supports to keep it well above the ceiling tile. Alternatively, cable may be hung with a variety of cable hangers, clips, and tie wraps from supporting structures. In some installations, particularly old work, the cable is laid on top of the ceiling tile supporting grid. Large buildings frequently have the cable placed in cable trays suspended between the ceiling grid and the floor above. This method is becoming more popular for Cat 5e and 6 installations, where the slightest kink or sharp bend can impair the cable performance. Any combination of these methods may be used as well. The routing methods are important because the more orderly routings inevitably require more wire. For example, routing through cable trays involves a lot of right angles instead of diagonal runs, demanding up to 40% more cable. And on the other hand, laying the cable directly on top of the ceiling grid with direct routing uses the least amount of cable, although it is the hardest to maintain and may suffer EMI problems more often. Cable trays are easiest to use during construction build-outs when the ceiling grid is not in place, but are more difficult to add once the offices are constructed, or worse, occupied. Trays carry significant weight from the many cables that they contain and must be well secured in place. For that reason, cable hangers and clips are often used to minimize disruption to an existing workplace. To estimate the orthogonal wire placement where cables are to be bundled or laid in cable trays, you must calculate the length of run in the tray, and this may involve a straight run or more than with several corners. Add each length of the run in the tray, and then next add the drop from the tray to the wall header above, the workstation outlet, and the lengths of the vertical drops in the workstation wall and the telecommunications room. Then add a factor of for obstacles 2% to 5% depending upon the building. Obstacles that might be encountered are HVAC units, ductwork, firewalls, columns, and pipes. The vertical drop should allow for 18 inches of excess wire at the wall outlet plus a distance through the wall to the height of the cable tray, not just the ceiling height. The vertical drop length into a telecommunications room should include the drop from the tray to the final termination point of the cable, including all ducts, ports, channels, and trays through which the cable must be routed. Be sure to accurately estimate the twists and turns the cable may take to dress the wires on the mounting board or in the equipment racks. Allow another 6 to 12 inches here for termination. If your measurements are close to the limit, remember that cables are typically routed along the length of a patch panel to their termination points, which might add up to 19 inches of additional length. Diagonal wire placement is really direct routing. Now this means that the cable is simply run above the ceiling grid, routed directly from the workstation to the drop location. Routing is done either directly over the grid or through supporting structures. And sometimes wire hangers or clips are used, as are some tie wraps. The use of cable hangers and clips may allow a combination between orthogonal wire placement and diagonal placement. Bundles of cable are typically routed through cable hangers orthogonally from the telecommunications room to groups of work area locations, but individual work area drop cables may be diagonally routed from the nearest hanger. Older buildings, houses, or buildings with fixed ceilings present special problems to cable routing. Often the cables may be run in an attic or crawl space. Sometimes cable may be run around baseboard or even over door frames to reach the workstation location. The use of staples, a common mounting technique for telephone wires, is definitely out, even for Cat 3 cable. Be careful when estimating cable lengths for these buildings. Simple detours such as doorways can eat up a lot of cable. For example, a 10 by 20 foot room would require 10 plus 20 plus 17 for 47 feet of cable simply to run to an opposite corner of the room. And if one 7 by 3 foot, which is 7 foot by 7 foot by 3 foot doorway, has to be traversed, if a drop must be run through several adjacent rooms to reach from the wiring closet to the work area, and then an enormous amount of cable may be required. Now we have to look at accessibility and appearance. The wiring centers of your network are key components of your LAN system, containing important networking hardware, the cable distribution points for your users, and important diagnostics and backup equipment. In addition, many important installation and configuration and troubleshooting tasks take place there. For those reasons, you should devote the time and money necessary to maintain good telecommunications room and equipment rooms. First key to a good telecommunication room is accessibility. The wire connections and network hardware should have their own room out of the way and yet easy to get to. The area should be as close to the work areas as possible, since LAN workers will often have to travel between workstation locations and the telecommunications room. That means that a location down the hallway near the elevator is not as useful as a small room or office near the work areas. The room should be used exclusively for LAN wiring terminations, hubs, routers, servers, and related equipment, but never for storage. The second key is appearance. The telecommunications room should be orderly, well laid out, and well lighted. Adequate power and ventilation should be available and designed for the specified purpose. Mounting boards in the walls should be full sheets of 3/4 inch plywood and well secured for the wall's interior structure. At least 2 walls should be plywood sheathed, and the board should be painted a neutral color such as gray. Areas for specific equipment should be well marked. If you use equipment rails or racks to mount your hubs and patch panels, they should be placed on a sufficient distance from the walls to work behind them. It is not at all a bad idea to place the hubs so that they can be viewed from the doorway or the telecommunications room. If you terminate the station cables directly onto a patch panel, you can use cable trays across the top of the mounting rails to route your cables. Wire management trays, mounting brackets, pre-assembled backboards, and distribution rings are available to help make a neat and serviceable cable arrangement. Proper routing or dressing of cables will make a neat, orderly appearance that will save maintenance time and trouble in the long run. Cat 5e through 7 wiring requires special precautions in installation and routing. The cable must be treated with great care during installation to preserve its performance characteristics. And the special care includes running the wire with a minimum of sharp turns, no stretching, no staples, and no tight tie wraps. Many patch panels have additional strain relief points at each cable termination to eliminate sharp bends and to help secure the cables with a minimum of stress. The third key to a successful telecommunications room installation is security. Equipment located in the wiring closet needs to be secured. That is one reason why a separate room with a locked door is the best location for your telecommunications room. If your telecommunications room is located in a common area outside your offices, controlling access is definitely essential. telecommunications rooms that are within your offices still may need to be secured, particularly in a high traffic location. Your company's mission may also dictate a need to control access to the room because important servers are often located there, in addition to the networking hubs. Size requirements for your telecommunications room. Telecommunications rooms need to be large enough to provide a proper area for wiring termination, patch panels, and hubs. In some cases, other networking equipment will be located in the same area. Rooms containing network hardware, such as servers, bridges, and routers, are properly called equipment rooms. And these ERs may be combined with telecommunications rooms at any level, including your MCs, ICs, and TRs. These space requirements for wiring closets are clearly defined in the EIA TIA 569. Minimum size for TR or IC is 7 by 10 foot. Now this space is designed to serve a 5,000 square foot area. A minimum size for an ER is 150 square feet. Now, as the table shows behind me, the sizes for other served areas. Now note that the metric conversions are greatly rounded in this standard. This is referred to as a soft conversion, and you should use the dimension in the appropriate unit of measure for your normal building plan dimensions. These sizes are really minimums, but should be adequate for most instances. In the case of equipment collocation with wiring closets, you will need to adjust the size of the room accordingly. Now remember that you need to have space in front and back of the racks, rails, and servers for routine maintenance in the wiring closet. While you are tempted to put the recommended area into a narrow space, remember that your LAN workers, installers, and vendors will have to work in that area and will be hampered by too small a space. Power requirements for telecommunications rooms. Many telecommunications rooms have networking equipment that will require electrical power. Power outlets for telecommunications rooms should be on dedicated circuits. A dedicated circuit is one that serves only one outlet or a series of outlets in one room. Standard practice in the United States is to equip each dedicated outlet location with a bright orange outlet, either a duplex or a simplex receptacle, to distinguish it. The electrical circuit should be rated appropriately for the equipment that is to be connected. Some larger equipment may require its own separate dedicated outlet. You should be sure that an adequate number of electrical outlets are provided based on the equipment that needs to be installed. Racks or banks of equipment may need an outlet strip or a power bar with multiple outlets. Allow lots of room for growth. A good rule of thumb is to provide twice the number of outlets that you think you'll need, and double that number. Remember to include open outlets that can be used to provide power to test equipment. The standard recommends 2 dedicated duplex outlets. AC outlets for equipment power rated at 15 amps or for 110 volts or appropriate ratings for your locality on separate circuits. It also recommends convenience outlets, wall mounted every 1.8 meters or 6 feet around the telecommunications room, in addition to any power requirements for the collocation of an equipment room. Also specified is lots of ceiling mounted lighting. Equipment rooms should have enough HVAC capacity to maintain the room at a temperature of 64 to 75 degrees. Another item to consider is power conditioning and backup power. Your power connection should, at the minimum, contain surge protection in areas that are subject to power line fluctuations. You might want to consider a photoresonant transformers that automatically compensate for sags and minor surges. True power spikes must be dealt with by the use of line surge protectors. Several types of these exist, including gas discharge protectors, semiconductor protectors, and metal oxide varistors. The metal oxide varistors are the most common and the cheapest and provide the least protection, usually found in low-cost multi-outlet strips. Their primary drawback in such an application are their slow response time and the user's inability to determine if they've lost protection because of prior spikes. A form of spike also occurs as a result of telecommunications wires that run outside your building. The most common occurrence results from a nearby lightning strike. Electrical surge may introduce destructive voltages in an outdoor cabling, including telephone and LAN cabling. It's very important to provide approved protectors on all telecommunications cables at the point of entry to your building. Fiber optic cabling with no metallic members can be an important tool in eliminating lightning risk. Another potential power problem is power outage. Equipment that might be disrupted by power outage should have emergency backup power supplies provided. Now these power supplies usually connect between the equipment to be served and the AC power outlet. One type of uninterruptible power supply, or UPS, is the backup UPS. When power is cut off, an inverter generates AC voltage from power stored in batteries. The generated power is switched to the connected equipment in a relatively short time period so that the equipment sees only a small break in voltage. Another type of supply, the true uninterruptible power supply, constantly generates power to the connected equipment. When there is normal line power available, the true UPS uses the AC line as its source of power. If there's a break in AC power, the UPS switches almost instantaneously to the battery source with no appreciable interruption in voltage to the connected equipment. As you might expect, a true UPS is considerably more expensive than the backup UPS. So what type of equipment should be provided with emergency power? Well, you should provide for equipment needed during an emergency or equipment that can be harmed or disrupted by a power outage. Equipment needed in an emergency might include the telephone system, the alarm system, or video security, or any network servers and hubs needed in an emergency. Some servers and other computer hardware are disrupted in a power outage and often must be manually restarted or cleaned up before normal use can resume. Emergency power, while temporary, may eliminate the restart process completely in a brief power outage. Some UPS systems alert servers to begin the shutdown process automatically. If it appears that the outage may be sustained, it also may be necessary to provide emergency power to network hubs to assist in the shutdown process. Unless user workstations are somehow provided with emergency power, it may be of little use to provide such power to the hubs and other networking equipment. So backbones and concentration. LAN backbones and cabling backbones unfortunately share a common name. During most of this book, we have been referring to backbone cabling rather than LAN backbones. However, in this section, we'll actually be talking about the type of logical backbone that are used in LAN systems. LAN backbones are often used to tie sections of the networking system together so that workstations anywhere on the network can use resources, such as servers that are not exactly in the same portion of the network. The workstations in a work area are connected to a hub-type device in the wiring closet. Hubs may be interconnected in a variety of ways, but often they are connected to a higher level of network called the backbone. In a classic repeater backbone system, as shown here behind me, we have several standalone 10100 hubs that are connected together via a 10-base-2 coax segment. Now, alternatively, these days they would be connected via a 1000 base T or a fiber optic, or at 100 or 1000 base F. Now this setup has the advantages of 100 base T star wiring to the workstations, but the disadvantages of a single backbone bus cabling between the hubs. Now if any hub or backbone link connection fails, the entire backbone segment is then likely to fail. Now as the figure shows behind me, we have another alternative. Now here the hubs are connected to a higher level backbone via 1000 base T, because all hubs repeat the LAN signals to all ports, and the servers can be located anywhere. Now some variation of this scheme put each hub into a circuit card that mounts in a hub chassis. The hub cards are interconnected at the back plane on a high-speed bus that is independent of the topology of the network. This bus serves as a type of backbone to all the hub cards. However, neither of these really tends to break up the network into smaller, more efficient chunks. Any network traffic is repeated through all the connected hubs, effectively limiting the bandwidth of the entire network to a single 1 gig path. As the figure shows behind me, we have several hubs connected via switching bridges or routers to a backbone LAN. Now notice that the servers in the local hubs are available to the local workstations without transiting a bridge. This effectively makes a 1000 meg bandwidth of a hub of hub A add to the 1000 meg bandwidth up to hub B, as long as the user on one hub has no need to use a server on the other hub. If a user on either hub needs to have access to a server on the backbone, the user connects across the intervening switching bridge. Company-wide applications are often placed on servers on the backbone to give access to any user without putting traffic on other parts of the network. Thus, a user on hub A can use a backbone server at the same time that a user on hub B uses a local server. As this figure shows behind me, a variation using a multi-port layer 3 router or switch. This type of backbone hierarchy must be considered in planning the location of telecommunication rooms, equipment rooms, and cabling between them. Repeater backbones and bridge backbones can both be supported by using the wiring standards that we've covered in our books. However, the specific number of interconnecting cables between telecommunications rooms may be dependent on the way that you lay out your backbone system. Switch hubs are often placed in separate telecommunications rooms. And this means that the LAN backbone cabling must be run between the telecommunications rooms to interconnect the switch hubs. These connections between telecommunication rooms are traditional backbone cabling. And the actual backbone switches may be placed together in the same equipment room or located individually at each hub that is to be connected to the backbone. In some LAN backbone topologies, a backbone must be formed, linking each telecommunications room. Token ring and FIDI are examples of this backbone ring method. Now, unlike the telephone scenario, the LAN backbone connections do not simply combine individual station cables into larger multiplier cables. LAN backbones usually require one backbone connection for each group of hubbed workstations that is to be connected. Additional backbone cables may be run to provide backbone for the primary cables or to provide closure of a ring. Backup cables or cables to complete a ring are an integral part of the backbone hierarchy. And by the way, nothing in this implies that a backbone is either fiber or copper, as either one can serve your needs. Now keep in mind that the allowable distance between closets in the 569B standard exceed the distances for copper wire. The 10, 100, and gig base T or token ring set without reference to a specific LAN topology. However, the use of fiber optic cable can extend your cables to the limit of the TIA standard. Now that's it for Chapter 14. So go ahead and move on to your online assessments, and then I'm going to see you in class. See you.